Hello, everybody. So hopefully we did okay with the graphing or finding limits graphically and by a table. As of this morning around 9 o'clock, I'd saw a little over half of you had finished, and today's Wednesday, by the way, a little over half of you had finished the Delta Math assignment. So if you haven't done that yet, get that done. Okay, those are going to be graded. But we found that the Delta Math is working pretty well because we don't have to do redos because it automatically gives you a ton of problems, which is nice for us as the teachers. All right, so we are talking about limits analytically or algebraically. All right, so here first off are some limit properties. These are pretty straightforward. It's saying that if you take the limit of f of x as x approaches c, and it equals this value of L, and then we have another function g of x as it approaches the same value, and it equals this value, then all of these properties just basically say, hey, take those two answers and use the property. That's pretty much it. So if you have a function a of x and you're approaching 5 and its limit's 4, take a different function b of x but approaching the same value, its limit's 3/2. Well, what's the product of that limit? Well, all you need to do is take 4 times 3/2. 6. That's the limit. That's what all of these rules state. If you know any two limits, you can just take the solution, those limits itself, and use the operation. All right. So, oh, there's my dog. Say hello to Scruffy, everybody. Let me pause this and calm him down. All right. So apparently there was a van outside. You know. Oh my gosh, the van's still there. All right. Okay, I think he's done. Okay. Oh my goodness. Sorry. Oh my goodness, the dog's crazy. All right. So, like I said, this is 3 days worth of material. So if at any point you want to just stop and do a couple of these at a time per day or knock it out in one day, that is up to you. We won't be posting anything new until probably Tuesday of next week. Okay, so finding limits algebraically. Now, you can always find a limit graphically. Okay, I'm not going to deny that. But we normally on a test have you do this without a calculator. So now we can't monitor that. So you will be expected to show every single step on these problems, okay? So that we know that you did these actually algebraically. All right, so part 1, direct substitution. Oh, another thing, the Delta Math didn't have everything that we wanted for assignments, so some of the homework will be on Khan Academy. I will not be checking this, so I highly suggest that you do this though, because you're going to need to do it on a quiz or a test, but I'm only going to be checking the Delta Math information. Okay, so direct substitution. You can use direct substitution for continuous functions where there's no holes, jumps, breaks, or graphs. It's valid for all polynomial functions. This is a polynomial function, guys. It works on rational functions whose denominators are non-zeros. And so these are both rational right here. This is irrational, this is rational. One of them works, one of them doesn't. And we'll talk about that after we talk about what direct substitution is. It means directly substitute your value you're approaching into the function. All right, so we want to know what is the value approaching when x approaches 1? Or what's our y value approaching when x is approaching 1? So you directly substitute it in. Literally, that's all it is. 3 times 1 to the third minus 2 times 1 squared plus 4. So what's that give us? So we got 3 minus 2 plus 1, or plus 4. Our limit is 5. So as from the left and from the right, the graph is going towards 5 for the y. Okay, it works okay with this one too. We have 1 squared minus 4 times 1 plus 2. We have 1 minus 2. I'm going to get a negative 1 over a negative 1. So the limit is 1. So as x approaches 1, the y is approaching 1. Okay, well, where it does not exist is if we tried to use direct substitution in this problem, I end up with a 0 in the denominator. So negative 2 squared is 4, 4 minus 9, negative 2 plus 2, end up with a negative 5 over 0. That doesn't work. Okay, one of two things is happening. Either the limit, oops, I don't know why I put 0 in there. That doesn't work. Either the limit itself does not exist, or we need to algebraically modify the problem so that we can find it if it does exist. All right, now I will tell you that this one actually does not exist itself. Okay, the limit does not exist. If we graph it, if you took a look at the graph, I think the graph goes like this. So as you're approaching it from the left and approaching it from the right, they're headed in different directions. So this limit does not exist. I am going to come back to this one in a second though, because that brings us to the next problem. What if direct substitution doesn't work? If direct substitution doesn't work, then we can try a variety of different things. First off, factoring. Okay, but always try direct substitution first. Okay, so if I use direct substitution in this problem, because we're going to try it, I have 4 squared, which is 16, minus 2 times 4, which is 8, minus 8, over 4 squared, which is 16, minus 20 plus 4. I get 0 over 0. 0 cannot be divided by anything, including, or excuse me, you cannot divide by 0, including itself. 0 divided by 0 does not exist, okay? So that didn't work. 4 doesn't work. Well, doesn't mean that it doesn't have a limit, though. Let's just go ahead and factor this guy. So I have an x minus 4 and an x plus 2. And in the denominator, I have an x minus 4 and an x minus 1. So what happens is these cancel, because what's happening is it's causing a removable discontinuity. Now I can plug in the 4, so I plug in 4, and I end up with 6 over 3. So my limit is 2. So what is happening with the graph is that, again, there may not be a value of 4, but it's still approaching something. That's what limits are. What is it approaching, not what is it equal to? So if I graphed this function, let's see. So if I graph this function, I think it would look something like this, where at 4, there would be a tiny hole in the graph, but it's still approaching 2. So as I'm coming from the left, approaching 4, hit that third time there, and then coming from the right, approaching 4, the y value is headed towards 2. So it does have a limit. All right, so we try the same thing here. You plug in 1. We get 3 minus 1 minus 2, that's 0 over 0. Again, doesn't work. So let's go with the factoring route. So I have 3x, x, I need a minus 1 plus 2, x plus 5, x minus 1. So those guys cancel. So again, I have a hole at negative 1, or I have a hole at 1. But that means that it's approaching. So I plug in my 1. So I end up with 5 over 6. Yeah, okay. So my limit is 5/6. Okay, so next. Back here again on the factoring, again, they have a Khan Academy. And here's the third Khan Academy that we are looking at. Okay, so once again, always try direct substitution first. Approaching 0. Oh, plug in a 0. I get a 0 in the denominator. It doesn't work. I get 0 over 0 again. Okay, so this might be something new. So what we're going to try is what's called rationalizing the numerator. Okay, we've done rationalize the denominator. So at any point, you can always rationalize the numerator or denominator to algebraically move it forward. So we're going to multiply by the conjugate of this radical, which would be the square root of x plus 1 plus 1. And we're going to do that down here as well, x plus 1 plus 1. All right, so the reason we can do that is because this is equivalent to 1, and anything times 1 is itself. So, it's not really changing the problem, but yet it is. Okay, so we distribute. Root x plus 1 times x plus 1 is x plus 1. Outside, I get a positive square root x plus 1. Inside, negative square root x plus 1. Last is a minus 1. Denominator, I'm going to go ahead and leave it because it could, in fact, be factorable, or we eventually would have to factor it, so just leave it in its factored state. So up at the top, the numerator, I'm only left with x. So my denominator, I'm x times x plus 1, square root of that, plus 1. And this is why we leave it in the factored state, because now these x's will cancel. and I'm left with 1 over the square root of x plus 1 plus 1. Now will direct substitution work? Now can we take the limit as x approaches 0 of this function? Yes, we can. 1 over 0 plus 1 is 1, square root of 1 is 1, so we end up with a limit of a half by plugging in 0 in for my x. So 0 goes in for the x to get me a half. All right, any questions, anybody? No? Okay, moving on. All right, limits for rational functions. So we did this actually in Unit 1 where we were talking about end behavior. So remember with end behavior, so we have the limit as x approaches infinity, or the limit of a function, the limit of a function. I don't know why I put that line there. Eraser. As x approaches negative infinity. Okay, now, again, this is what I'm talking about for infinite limits. This is an infinite limit. It's approaching infinity. The other examples I was giving you was approaching a number. When it's approaching a number, you direct substitute. If it doesn't work, try factoring. If that doesn't work, try rationalizing. Okay, but this is approaching infinity. So infinity has rules, people. There's rules. So we did rule infinite functions of polynomials. Okay, so like 3x to the 4th minus 5x squared, or that was our function that we're using. So let me get rid of that because that's the function. Or say we have 5x to the 3rd minus 2x squared plus 1. So this is end behavior. So remember with end behavior of polynomials, what you did was you took a look at the Lie coefficient and the degree to determine which direction the graph opens. So in this problem, meaning that it's an even degree with a positive Lie coefficient, I know that the graph, the left and the right are both going to end up. I don't, what's ever going on there doesn't really matter. So I would know that the end behavior, so the limit as x approaches infinity, would be, so my right side would be infinity. When it was an odd degree, positive Lie coefficient, I know that the left ends down, the right ends up, blah, 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 what goes on in here. So when I wanted to know what the left side was doing, well, the left side went down, so this would be a negative infinity. So that was the rules for polynomial functions. If it was a rational function, meaning a fractional function, then you have these 3 rules that you have to follow. It's still based off of the degrees, but we have the degree of the numerator and the degree of the denominator are the same. When that happens, you divide the Lie coefficients. When the degree of the numerator is less than the denominator, it's always 0. For these two, the rule's the same. It doesn't matter if the limit is approaching positive or negative infinity. The rule is the same. Okay, for the third one though, when the degree of the numerator is higher than the denominator, it is a plus or minus infinity, so you have a 50-50 chance. But the slant asymptote and the sign depends on the Lie coefficients. Now, we're not going to get quite into the slant asymptotes, but I'll show you a way that we can figure this out by the signs. Okay, so we got the next example of each case here. All right, so case 1. Case 1 is when the degree of the numerator is equal to the denominator. When that happens, you divide the Lie coefficients. So the limit, negative 2/5. Simple as that. Second example, when the Lie coefficient, whoops, that's not the, oh yeah. So when the Lie coefficient, or excuse me, when the degree of the numerator is less than the degree of the denominator, 2 is less than 4, it is always 0. Again, it wouldn't have mattered if this would have been a negative, and then it wouldn't have mattered if this would have been positive. It's the same answer. Okay, but for the limit of z as approaching infinity, when the degree of the numerator is greater than the denominator, this is what we're going to do. We're going to take a look at those Lie coefficients, okay? So I have a z to the 6th, and I have a negative 5z to the 3rd. Because this is going to approach what's called a slant asymptote. It's a line that it's approaching. We are going to take a look at what happens. So the idea, if you think about the substitution, is that you are plugging in values for z. Okay, now the reason that the Lie coefficients are the only thing that's important is because it's this idea of a slant asymptote that we are trying to follow. So here's the idea that I want you to think of. Okay, we're going to plug in positive numbers. Okay, so just as the numbers are getting bigger and bigger and bigger, and think about how the signs of these work. I'm taking a huge positive number, and I take that to the 6th power. Then I have a negative number. Okay, I have a negative number times, well, I'm plugging in a positive number to the 3rd power. Okay, so let's think about this. What's a positive to an even number? It's still going to be positive. Okay, now that's my Lie coefficient. That sign's still going to stay. But what's a positive to an odd power? It's still positive. All right, well, I have a positive number up top. What happens when I take that negative Lie coefficient and I multiply it by a positive number? I end up with a negative number. What's a positive divided by a negative? Negative. So this goes to negative infinity. Negative infinity. Makes no sense? Okay, let's try some more. All right, so degree 2, degree 1. So degree of the numerator is greater than the denominator. All right, I have a negative Lie coefficient, x squared, and an x. All right, so I'm taking the negative 2, it's just a negative number. And now what's happening is I'm plugging in, I hate it when I think I hit the highlighter. I am plugging in negative numbers. Okay, I'm just going to, it's approaching negative infinity. These numbers are going to continually get smaller and smaller and smaller and smaller. Okay, so I'm plugging in negative numbers for x, but I'm squaring that. All right, now I'm taking a look at this, and then I have a negative number. Whoops, not negative 1. It's just a negative number. Okay, I'm not taking it to any power. All right, so I have the negative Lie coefficient up top. What's a negative squared? A negative squared is a positive number. And in the denominator, I have a negative. What's a negative times a positive? A negative. What's a negative divided by a negative? A positive. So what's happening is this is approaching positive infinity. Okay, hoping this is making sense to you guys. So let's look at this one. Okay, now we are going to want to make sure we multiply. You don't actually have to multiply out the whole thing. The only important thing is the Lie coefficient parts. So the Lie coefficient would be a negative 12x to the 5th. Here, if you want to distribute, you can go ahead and distribute, but really what's going to make it the degree is, well, the highest value times the highest value. So I'm going to multiply those two, and x times a negative x to the 3rd. Okay, so that's what's important. That's where the direction is headed towards. The back end of this function doesn't adjust where it's headed towards. Okay, the main part's coming from the Lie coefficients. All right, so we have degree of the numerator is greater than the denominator. All righty, so we are headed towards negative infinity. So I have a negative Lie coefficient. The negative 12 is negative. I'm taking a negative number to a 5th power. Okay, the denominator, I have a negative Lie coefficient, and I'm taking a negative number to a 3rd power. So I have my negative Lie coefficient. What's a negative to the 5th? It's still going to be a negative number. Any negative to an odd number is going to remain negative. Okay. All right, and then I have a negative Lie coefficient and a negative to a 3rd power, which is still going to be negative. What's a negative times a negative? A positive. What's a positive times a negative times a negative? Positive. What's a positive divided by a positive? A positive. So this is headed towards positive infinity. Okay, it's just a coincidence that both these negatives gave you a positive value. It doesn't always happen that way. All right, now, like I said, it will, or maybe I didn't say it, I can't remember. On Delta Math, when it is approaching infinity or negative infinity, it'll actually tell you to put in do not exist. Okay, so I would highly suggest you practice with these. When you get your review, it won't be does not exist. It will be positive or negative infinity. So make sure you know how to use the sign rules. All right, piecewise functions. Where are we at in terms of notes here? I'm getting tired. All right, 19 minutes. That's shorter than the other one so far, I guess. All right, so you do have a Delta Math assignment on this one. Okay, so make sure you do that one because that one is graded. Okay, so piecewise functions. We actually did this, well, I feel like we did this a little bit because we had piecewise functions on the actual graphs. But remember that for something to have a limit, the left side and the right side have to be the same value for the limit to exist. So when there's not a directional here, it doesn't state x, x approaches 1 from the left or x approaches 2 from the right. It's just saying 1. All right, so the left and the right have to be the same. So coming from the left sides are smaller numbers. So the left end behavior limit would be the limit of this function as x approaches 1 from the left means you're using the x squared function. Because the left side of 1 is the smaller than 1 numbers. So we're going to plug 1 into that function. So when we plug 1 in, I get 1. Then I'm going to look at my right end behavior. So the limit of x, oops, not necessarily x squared. The limit as x approaches 1 from the right. Well, from the right side, that means that the x values are greater than 1. All right, so you didn't lay down very long. You didn't lay down very long. No. Oh, well, I'm just finishing my videos. Sure. I'm getting Culver's, so you don't want it. Excuse me. Okay, so what we're going to do, again, doesn't look like it, but what we're going to do is we're going to approach 0. We are going to multiply this by a value equivalent to 1. So I'm going to multiply it by 5 over 5 because I picked that number because of this guy. And then I have sine of 5x over 5x. All right, so what I can actually do is apply the constant rule. So if you go back to page, what was it, 2? Yeah, page 2, the constant rule here. When I have a value times a function, that is just going to be that value, the k value, times the solution to the limit of that function. Okay, you're like, what? What? All right, so this means that I'm going to be able to bring this constant out to the front. So I have 5, you write that, 5 times the limit of x approaching 0 of sine of 5x over 5x. Okay, so this rule applies to any matching values here. So if it's sine of theta over theta, great, that's equal to 1. If it's sine of 5x over 5x, that's going to be equal to 1. So I have 5 times this limit is equal to 1. So my answer is 5. Okay, so same type of deal here. Now this isn't exactly like this. Okay, so cosine of theta minus 1 over theta is not the same thing as 1 minus cosine of x. It's close. Okay, so I just realized I forgot to change my notes thing, because on your notes you should have a square here. Okay, so 1 minus cosine of x over x squared. So we're going to apply, again, a conjugate rule for this in order to move this progressively forward. So what I'm going to do is I'm going to multiply this by 1 plus the cosine of x and 1 plus the cosine of x. So that gives me 1, the outside inside will cancel, minus cosine squared of x over x squared times 1 plus cosine of x. What is 1 minus cosine squared of x? Oh no, we have to remember our trig. It is sine squared of x over x squared times 1 plus cosine of x. All right. Okay, so still the limit. If we keep plugging in zeros here, I'm still ending up with 0. Okay, what's going on here? Well, we can still progressively move forward with this guy and separate it into separate fractions. All right, so we're going to end up with the limit as x approaches 0 of the sine of x over x times the sine of x over x times 1 over 1 plus cosine of x. Okay, it's still sine squared of x over x squared times 1 plus cosine of x, but based off of this function, I know that this limit is 1. I know that this limit is 1. And now I can plug in the 0 for cosine. And once again, what's the cosine of 0? 1. So we end up with, whoops, this was supposed to be a product there. So I have 1 times a half. So the limit, a half. Okay, so again, I just don't want it to automatically assume that these two special cases will always be used, because that's not the case. All right, and last page. Okay, composite functions. I left this one on here because I actually just got tired of typing and I didn't want to type anymore. So you have an extra optional video for instruction on this one, but basically this composite of limits, it's just like how composites work. You're going to find the limit of the first function, take the limit of that first function, and then that becomes the new limit of your second function. So that's what this composite is. The limit of f of g of x, or the limit of f of g of x, two ways to write that, just means that you're going to take the limit of the first function at this, but then that answer becomes the new limit of the second function. Okay, so I'll just rewrite this. The question was saying find the limit of the composite f of g of x as x approaches 4. So first thing we're going to do is find the limit of the g of x function as x approaches 4. So I take a look at my g of x function, and at 4, well, we're going to have to factor that guy. This one's from the previous example, way up at the top. So I do have to factor that because right now the 4 gives me a 0. So I'm going to get an x minus 4 and an x plus 2. Denominator is an x minus 4 and an x minus 1. Those cancel. So I get 4 plus 2 over 4 minus 1. So my limit is 2. So now you're going to find the limit of the f of x function as x approaches 2. So that's how that works. So I plug 2 in. 2 also gives me a 0. So I have 2 minus x over x minus 2 and x plus 2. Okay, so once again, the 2 gave me a 0. Now these are close, not exactly the same, but they're close. 2 minus x and an x minus 2 reduced to a negative 1. So that gives me a negative 1 over x plus 2. Now I can plug the 2 in, and I get a negative 1/4 limit. All right, so again, please, if you have questions, email me, or let's set up a Google Meet and go through anything, but you are going to have a test on this. Okay, you have to get 60% or better for me to say that that test counted. It's like if you were absent and then you just didn't take that test. Okay, that is an incomplete for the class. Just because we're on remote learning doesn't mean that you guys can't be trying on these problems. All right, so make sure you are doing what you're supposed to be doing. We only have 2 weeks left after this week, so we're getting close to the end. All right, talk to you guys later.